Okay, so in the last video we saw this result. Now let us prove this. So here what we are given a connected graph G and there is a spanning tree T in G. We already know that in any connected graph we always have a spanning tree. In fact, much more is true. If you choose some specific vertex in such a connected graph and then you try to find a spanning tree, you can then find a rooted spanning tree with that vertex as its root. But anyway, you will find a spanning tree. Now, corresponding to this spanning tree, there will be fundamental cycles and fundamental cuts of the graph. And these fundamental cycles will form a basis of the cycle space of the graph, and the fundamental cuts will form a basis of the cut space of the graph. And in fact, if the graph has n vertices and m edges, then the dimensions of these spaces are given by those relations. So let us recall what fundamental cuts and fundamental cycles are. So say you have your connected graph G in which you find some tree, a spanning tree, some sort of spanning tree, something. The tree is spanning because it will have all the vertices of the graph, but not necessarily all the edges of the graph, of course. If the graph itself is a tree, then obviously the spanning tree will be equal to the graph. But if the graph has cycles, then you will have to remove some edges in order to get rid of those cycles so that the skeleton you are left with is a tree. So that's the spanning tree. Now, for every edge in this spanning tree, if you remove, say this is an edge E, if you remove this edge, that is if you consider the graph T minus E, then this T minus E has precisely two components. You can see that here. This is one connected component and this is the other connected component. Now between them the edge E was there before we deleted E. But if you think of this entire thing inside the actual graph, in the actual graph also maybe there were some edges which we deleted in order to get T from G. So if you think of those absent edges along with this E, of course, then whatever may be there in the original G, those edges, not all the edges of course, those edges that have one end in this component and the other end in that component, that kind of edges, including this edge E also, then that set of edges which we have already denoted in the previous video by DE forms a bond. It is a bond in the graph. So these bonds are called the fundamental cuts of the graph with respect to this spanning tree T, and you will get one such bond for every edge E in the spanning tree. Now, instead of the edges in the tree, if you consider the edges in the graph that are not in the tree, okay, so let me draw this once more. Say that exact same tree. Okay, so this was our T. Now any edge that you may have in G but which is not in T can now be introduced, so that the tree will no longer remain a tree. It will now contain a cycle. Say, just for the sake of seeing what would happen, say in our original G, these two vertices were adjacent, so that there was an edge between them. We deleted this edge to get T along with some other such deletions. So now let me introduce this edge. Say this edge is E prime. So here what you are looking at is T plus E prime. Then naturally this T plus E prime has precisely one cycle, this cycle, and that cycle we call CE prime. You will get exactly one such cycle for each edge in G that is not in T. That means for this kind of edges, which are edges in the actual edge set of the graph, but which are not edges in T. And such cycles are called the fundamental cycles. These are the fundamental cuts, and these are the fundamental cycles. So the claim here is that the fundamental cuts, if you consider their set, that set becomes a basis for the cut space of G. Like that, the set of all fundamental cycles is a basis for the cycle space of G. So that's what we have to prove, and when we prove this, a consequence of that will be these dimensions also. So let us now see the proof. The proof is not very long. It is in fact reasonable, some lines. In fact, the proof is actually somewhat short. Okay, so the proof goes like this. Since every edge E belonging to the edge set of the spanning tree T is in DE. That means is an element in D. We can see that here. Here, these edges form the set DE, and among all those edges, E itself is also an edge. Since every edge E belonging to the edge set of T is in DE, but is not in DE prime for any E prime belonging to E of T satisfying E prime not equal to E. Because of this thing, DE is not a linear combination of the other fundamental cuts. Okay. Now there are two things to understand here. First is this claim. Why is it the case that E of course belongs to D, that we can see here, but why does E not belong to any other DE? that is other dE prime for some different edge E prime, again from T, but different from E. Why is that so? And the second thing to understand is that how does that imply this thing, that dE is not a linear combination of the other fundamental cuts, that is some other dE primes. Okay. Now, why does E not belong to dE prime? So, from this figure itself, you can see what would happen if in place of E you delete another edge, right? If you delete another edge, no matter what edge it is other than E, say you delete this edge, say, okay, then also you get two components in the resulting graph. One of them consists of all these vertices and the other component is this single vertex. Or if you delete, say, these edges originally are not part of E, we just showed them just in order to show what the edges in dE would be. Now, no matter what edge you choose for deletion other than E, you are always, for example, you can choose this one. Then also you will get two components. One of them is this path, ordinary path, and the other one is this tree. In any such process of deleting some edge other than E, E survives. E of course will be there even after deletion of this edge, say. Now, when you go back to G and see what edges originally are there in G between this component and this component, and between means again like that, those edges which have one end in this component and the other end in this component. Do you think any such edge can be E? Of course not, because E does not have its ends lying in different components. Why? That is because these components have been created by deleting that edge, which is some edge other than E. So, definitely the ends of E either will lie in one component or the other, okay, but never like this. And that is why E, now if say this edge which you deleted here is in fact your E prime, then if you go to G and see what original edges were in G that lie between this component and this component that you get after deleting E prime, then none of those edges is E. That's why E belongs to dE, fine, but at the same time E does not belong to dE prime for all E prime not equal to E. Okay, so this part is now clear. Why that specific edge E only belongs to the cut that is labeled by it, the fundamental cut, and no other fundamental cut. Okay, so now the second thing comes, why does this fact imply that dE is not a linear combination of the other fundamental cuts? Keep in mind that all these things are happening in the edge space of the graph, that is this space. What are the vectors in this space? The vectors in this space are sets of edges, right? Now, for example, this dE is one vector. All the fundamental cuts are elements in this edge space, that is, they are vectors in this vector space. And in this vector space, these are, do not forget that these are bonds, special types of cuts. And we already have seen that in the cut space, any cut is actually a disjoint union of bonds. Addition in this vector space actually is what? Symmetric difference of any two such vectors, which are strictly speaking which are sets after all. So you take their symmetric difference, but it turns out that those symmetric differences, due to the fact that the sets you are considering can be chosen to be disjoint, so those symmetric differences turn out to be just disjoint union. Because if you take the symmetric difference of, say, just to distinguish these things from this specific DE prime, let me call this DE1 and DE2. Because DE1 and DE2 can be chosen to be disjoint, so this is the symmetric difference of DE1 and DE2, right? So which just happens to be DE1 union DE2 because they are disjoint. So this is nothing but DE1, this is nothing but DE2. Okay. Now this is a specific fundamental cut which has E, which has the edge E in it as an element. We have other fundamental cuts also. For each edge in the tree we will have one fundamental cut. Now E belongs to DE and E does not belong to any other fundamental cut. So linear combination, taking linear combination amounts to considering disjoint unions. So if you take the linear combination of the other fundamental cuts, that means considering their union. So if E does not belong to any one of them and E only belongs to DE, then naturally their union would not contain E. That means you have an element E in DE which is not in this union. Which in fact is the linear combination of the fundamental cuts in the edge space which are different from this fundamental cut, and that's why this linear combination is not equal to DE. That's what we have here. DE is not a linear combination of the other fundamental cuts. And what does that tell you? And this is going to be true for every edge E in T. That means no fundamental cut is a linear combination of the other fundamental cuts. That means the fundamental cuts form a linearly independent set in the edge. In the edge space means in the cut space actually. We can consider the subspace itself. So that is the next thing we are going to write. Okay, so now I can erase this. Hence, the fundamental cuts form a linearly independent set in the cut space of G. Okay. Now in order to see how large this set is, you of course need to know precisely how many fundamental cuts will be there, how are we getting the fundamental cuts? For every edge in the spanning tree, we are getting one fundamental cut, and distinct edges are giving us distinct fundamental cuts. So what does that mean? That requires us to know how many edges there are in the spanning tree. Now you already know from the section on trees and forests that a tree with n vertices has how many edges? N minus 1 edges. The number of edges is 1 less than the number of vertices. And how many vertices are there in our spanning tree? Because it's a spanning tree, it should have all the vertices of G. So there should be n vertices in the spanning tree, and as such there will be n minus 1 edges in it, which gives rise to n minus 1 fundamental cuts. And we know that we have obtained a linearly independent set in this vector space having n minus 1 elements. So that means what? This means that the dimension of this vector space should be at least n minus 1. So in order to justify that we will have this many edges in the spanning tree, we have to recall that result from the section on trees and forests. And in fact, the author here continues this line like this: of size, the size of that set, linearly independent set, is n minus 1. And this is where we write, do I write simply corollary? Yeah, I can write. That's how the author has written it. 153. So this is the result which tells us, in fact the statement of this corollary is that a connected graph having n vertices is a tree if and only if it has n minus 1 edges. Okay, so that's the thing we are using here. Okay, thus the dimension of the cut space should naturally be greater than or equal to n minus 1. Similarly, every edge E belonging to the edge set of the graph but which is not an edge integer. So now we are going to consider fundamental cycles. Every edge this belongs to or is in CE, the fundamental cycle CE, which you obtain when you add this edge, introduce this edge to the spanning tree. The spanning tree has its own edges, but besides that you introduce this edge, and that creates precisely one cycle in the resulting graph, and that cycle is this fundamental cycle. So naturally that edge E is an edge in this cycle. So E is in this, but not in CE prime for any E prime belonging to this satisfying E prime not equal to E. So just like no DE is a linear combination of the other DE primes, no CE is a linear combination of the other CE primes. Hence CE is not a linear, the argument is exactly similar to that one, linear combination is not a linear combination of the other fundamental cycles. So the fundamental cycles form a linearly independent set in the cycle space of G. They also form a linearly independent set in the larger space H space of G, but specifically inside this, because all the cycles are going to be vectors in this subspace. Okay, now we come to the size of this set of all fundamental cycles. So how many fundamental cycles are there? For each edge here we have one fundamental cycle, and distinct such choices give us distinct fundamental cycles. So what is the size of this? How many elements are there? How many edges does G have? M edges. How many edges does T have? N minus 1 edges. So the number is m minus n plus 1. So we will have precisely this many fundamental cycles. So the set of all fundamental cycles has size this m minus n plus 1. Hence the dimension of the cycle space of G is greater than or equal to m minus n plus 1. Okay, but now we have that other result that we have already proved in the previous video, namely that the cycle space and the cut space are orthogonal complements of each other. And even before that we have seen one more identity, namely that if you have a subspace, any subspace F of the edge space of G, then the dimension of that subspace plus the dimension of its orthogonal complement F perpendicular is m, where m is the number of edges in G and is also the dimension of the entire space. Now think of the cycle space here, C of G. Now that result I was talking about, which we proved in the previous video, is that C perpendicular is nothing but C star. Okay, so we now have this thing. So let us now write the results and see what is the final conclusion of all these things. Now, and this result is a theorem. Now theorem 195 implies, let me write it a little more elaborately than how it's written in the text implies that C star of G is C of G perpendicular. So this is one thing. This is what theorem 195 says. Besides also saying that the orthogonal complement of C star is also C. Also, we know that the dimension of C of G plus the dimension of its orthogonal complement is M. So now you combine these two things, hence plus is equal to M. Okay, now you think of the inequalities. This number is at least M minus N plus 1. It can be higher. That possibility is here. And that other number, this is at least N minus 1. This one is at least M minus N plus 1. But the sum of these two numbers, it turns out, is equal to N. So that leaves us with only one possibility, namely that this inequality and that other one, actually they have to be equalities. Because if any one of them, say this one becomes larger than this, then the sum would exceed N, which is not the case, because the sum has to be equal to M. This sum has to be equal to M. So this must be equal to this and this must be equal to this. Thus, we must have and but what are these numbers? This is the number of all fundamental cycles and this is the number of all fundamental cuts. So it turns out that these numbers are now equal to the dimensions of the respective spaces. And also we have at least this many fundamental cycles in the cycle space, at least this many fundamental cuts in the cut space. But now because it can, these numbers satisfy these relations, so they are at most as well. That is, you have at least this many fundamental cycles, but you cannot have any more due to this dimension restriction. So the set of fundamental cycles is not just linearly independent, but it has to span the entire cycle space, and that is why it will be a basis for the cycle space. Similarly, the set of all fundamental cuts will be a basis for the cut space. Thus, the set of all fundamental cycles is a basis of the cycle space of G and the set of all fundamental cuts is the basis of the cut space of G. And this completes the proof. Okay, now in this final part of this section, we are going to introduce some matrices associated with graphs. Let G equal to V comma E be a graph, of course, with vertex set V and edge set E, where V has these vertices V1, V2, etc. up to Vn, and E consists of these edges. Okay, now we are going to define something known as the incidence matrix. The incidence matrix B, or to be more specific, that it's the incidence matrix of G, you can write B of G, is the matrix Bij. It's an n by m matrix, where n is the number of vertices and m is the number of edges. Defined as this. Now we need to say what Bij's are. Bij is defined to be equal to 1 if Vi belongs to Ej and 0 otherwise. Vi is, of course, this vertex, the ith vertex in this order of writing the vertices, and Ej is the jth edge in this order of writing the edges. Now Bij is defined to be equal to 1 if Vi belongs to Ej means what? It just means that Vi is incident with Ej, or Ej is an edge at Vi, like this. This is Vi, there is some other Vk, and this edge we are calling Ej. If this is the situation, then Bij is defined to be equal to 1. So Ej, strictly speaking, is this set Vi, comma Vk. That's why we write Vi belonging to Ej. You remember, edges are defined to be two-element subsets of the set of vertices in any graph, and if this is not the case, that is, if Vi is not incident with Ej, then Bij is defined to be equal to 0. So that is the incidence matrix of a graph. Now let us consider one example. Let's see what happens if we take an actual graph and calculate its incidence matrix. say this is my graph and let me name the vertices in any manner I want. Say V1, V2, V3, V4, V5, and well, just for the sake of showing one specific thing, let me just take two other vertices also and make it a graph like this. V4, V5, V6, V7, say. No, what the hell? I already have V5 here, so this will be 6, 7, 8. Now is it okay? 1, 2, 3, 4, 5, 6, 7. Yes, we have 8 vertices. Now let us name the edges also, because we need the edges also to be named. Let me call this one E1, E2, E3, E4, E5. So this is E6, E7, E8, and so this is E9. It looks a bit messy, but we will manage, we will see. Okay, so how many vertices are there? 8 vertices. And how many edges are there? 9 edges. So I purposefully considered this graph so that I can show that the number of vertices can be different from the number of edges. Okay. Now that means my matrix will be an 8 by 9 matrix with 8 rows and 9 columns. Okay, so now if we use just the definition of Bij, so 8 rows correspond to what? They are going to correspond to the 8 vertices. So the first row is going to correspond to the first vertex, and that means I will be now looking at B1j. Now B1j will be equal to 1 if and only if V1 is incident with Ej, but there is only one such edge, that is E1. So only B11 will be 1. B1 anything else is going to be 0. That is because B1 is incident with only this edge and no other edge. So I will now have, that means my B or Bg here, if this is, I am calling this G, then Bg is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. What about V2? V2 is incident with the first edge, second edge, and fifth edge. So 1, 2, 3, 4, 5. V3 is incident with only the second and third edge. That means only these two entries will be 1, the rest are 0. V4, 3, 4 and 6. 1, 2, 3, 4, 5, 6. This 1, 2, 3, 4, 5. 4 and 5. 1, 2, 3, 4 and 5. 6, 7, 8, 9. Okay. So we have written this for V5. Then V6, 6, 7, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. V7 only 7 and 8. 2, 3, 4, 5, 6, 7, 8, 9. And finally V8 is incident with only E8 and E9. 3, 4, 7, 8, 9. This is the incidence matrix. Okay, so it looks quite large. It depends on the size of the graph. Fine. Now let us see what else the author says. What the author says after this is this: as usual, let BT, B is the incidence matrix, BT denote the transpose of T, transpose of B, sorry. Then B and BT define the linear maps. B defines a linear map from the H space of G into the vertex space of G, and B transpose defines a linear map or linear transformation from the vertex set of G to the vertex space of G to the H space of G. They are linear transformations in the sense of vector spaces, because these are vector spaces. Both are vector spaces over the same field, the field with two elements, so you can consider linear transformations, and these matrices naturally give rise to linear transformations. But linear transformation in what sense? Under the standard basis of these spaces. You remember what the standard bases are? The standard basis of this space, the vertex space, is the set of all singleton sets of vertices in that order in which the vertices are originally written, and the standard basis similarly for the H space is just this. Now that means that if you consider, for example, a vector in the vertex space, what is that actually? That is a set of vertices, in other words, a subset of the set of vertices of G. So expressing that vector as a linear combination of this standard basis vector means expressing that set as a linear combination of these singleton sets, or as a union of these singleton sets. Now some of the sets will appear in that union, namely precisely those sets will appear whose elements belong to that set which you are expressing as a linear combination, and those VI's that are not there will not appear here in this linear combination. So once you do that expressing as a linear combination, you will get coefficients. No? Those coefficients are going to be either 0 or 1. So that will give rise to a matrix. That matrix is B. So the setup is like that. It is that linear combination whose matrix is B with respect to this standard basis. Just like that, this is that linear combination sorry, this is that linear transformation whose matrix under this basis is going to be the transpose of B. Okay, now after this, what the author does is that he gives some facts about these matrices. It turns out that these linear transformations have special kernels and images, and the result is very nice. It has just been mentioned. It is proposition 197. It has two parts. Part 1 is this. The kernel of this linear transformation B is nothing but the cycle space of G. So the kernel of B turns out to be in fact precisely the cycle space of G, and it makes sense also because the kernel is a subspace of the domain space. Here the domain space is the edge space, and this is a subspace of the edge space. And part 2 the image of B transpose is the cut space of G. The image of a linear transformation is its set of all values, set of all images. We already know for any linear transformation that is also a subspace of the second space. So that here is again the edge space. This time we get the cut space. Now these are claims that actually have to be proved. Now if you instead of thinking about a general proof, if you just think about why should this kernel be the cycle space. If you are going to take one vector from the cycle space and apply this linear transformation to that vector, are you going to get 0? Because that's the meaning of kernel, right? Let us do that for this example. Let's see what happens. This is V3. Okay. Now any vector from the cycle space means what? It is a cycle, or more specifically, it's the set of all edges in that cycle. So let that cycle be this cycle. Okay. Now keep in mind that we have to know how we are going to apply this linear transformation B. So naturally, when you define a linear transformation by a matrix, it means multiplying a vector by the matrix from the left side. That naturally, that's what it means. But vector means what vector? This vector. But you cannot, of course, multiply a cycle by a matrix. That is meaningless. We do not have that kind of operation. But note that before you do any such thing, you have to express this cycle as a linear combination of what? Of the standard basis vectors in the edge space of G, where the elements are what? The elements are the singleton sets consisting of the edges. Now what is your vector here? And the fact that I am saying that I am considering this cycle as my vector, actually what I am saying is that this is my vector Okay, this is when I say that I am considering this cycle in this cycle space, precisely this object is my vector, this set of edges in the cycle. Now if you express this as a linear combination of the basis vectors in the edge space, then that linear combination looks like this. And if you want to decipher this sum, then this is nothing but this. A3 union A4. That's what it is. Now, from this linear combination, if you write the vector in the actual Euclidean space, then the vector corresponding to this vector from the cycle space is going to be what? It is going to be a column vector. That column vector will be 0, 1, 1, 1, 1, 0, 0, 0. As many zeros there are after that. So you are going to then look at this column. One, two, three, four, 5, 6, 7, 8, 9. You have to multiply this column by this matrix. When you do that, that's what it means to apply this linear transformation on this cycle. Now, when you do that, what do you get actually? If you go row wise, I mean, you also have to actually multiply, carry out the multiplication. You will see that you are always going to get 0. Here, for example, this one is 1, and that precise element here, the corresponding element here is 0. Here everything else is 0, this is 0. What are you going to get in this second one? Yeah, that second one is important. See, everything lies here. In the second one, when you do the second one, and you are going to get 0 of course, but 1. If you write alongside this column, this row in the column form, what will you get? 1, 1, 0, 0, 1, and then 4 other zeros. Now, when you take the dot product of this as a row and this column, you are going to match the corresponding entries, multiply them, and then add the products. That is going to give you this entry. So when you look at the correspondence, you are going to multiply 0 with 1. Okay, that vanishes. You are going to multiply 1 with 1, that does not vanish. This one vanishes. This one vanishes. This one does not vanish. And these 4 of course are going to vanish. So when you do the multiplication and add the products, you get 1 plus 1. But keep in mind, you are in the 2 element field F2. So 1 plus 1 is going to give you 0. But that is a special case, right? We are looking at the second row, means the row corresponding to V2, and we are considering the vector representation of the cycle in our 9-dimensional Euclidean space. What would happen for the other things? Note that when you multiply a row with a column, that row corresponds to a vertex, some vertex here. So this vertex we have seen that here. So when are you going to get this kind of things that will give you 1? Precisely when this vertex is incident with such edges, also those edges that are coming from the cycle. Now when you consider this vertex and consider the edges that are incident or that are edges at this vertex, and also at the same time they are coming from the cycle, how many such edges will be there for each vertex? Precisely 2, because for any vertex on the cycle you are obviously going to have 2 edges at it which are coming from the cycle. So anytime you consider such a scalar product, row column, you are going to get 1 plus 1. That will give you 0 in the 2-element field. So that is why whenever you express a cycle as a vector and apply the linear transformation on that, you are going to get the 0, always 0. That is why all cycles, that is all vectors coming from CG are kernel vectors for B. That itself does not tell us that the kernel is CG. The kernel may be having more vectors, but this is where the dimension will play a role. It will tell you that precisely this itself is the kernel. In some such way you can make sense of this one, that the image of B transpose is C star G. It's just to show this thing that I kept this calculation. Now something else is also there after the incidence matrix, namely the adjacency matrix. Of G is the matrix Aij. Unlike the incidence matrix, it's an n by n matrix, whereas n is the number of vertices in the graph. Oh, we already have written matrix, no? Defined as so here rows and columns are both going to correspond to vertices. Not edges do not have any, well, they have a role here but not in that way. This is one if Vi and Vj are adjacent, that is when they form an edge in the graph, and 0 otherwise. So because this matrix keeps track of adjacencies, that is which vertices are adjacent to which other vertices, that's why it's called the adjacency matrix. There is one more matrix, the degree matrix. D or D of G of G is the diagonal matrix. Dij. This is also an n by n matrix. Because we have said that it's a diagonal matrix, so there is no need to define the off diagonal entries. They are going to be 0. Only we need to say what the diagonal entries are. And the ith diagonal entry is nothing but the degree of the ith vertex. And it turns out that these things, the incidence matrix, the adjacency matrix, and the diagonal matrix are related by an equation, and that is the last proposition. This is proposition 198. In the context of whatever we are doing here, this fact is there. The incidence matrix times its transpose is equal to the adjacency matrix plus the diagonal matrix. Now these final results about this type of matrices, about their properties, are parts of algebraic graph theory, which itself is a very vast subject. And the proofs of these things, the actual elaborate proofs, can be found there. The author seems to not have given these things any more space in the text. But it turns out that eigenvalues of these matrices are intimately related to the properties of the graphs from which these matrices are coming. Many results are there. For example, because the adjacency matrix of a graph is a real symmetric matrix, its eigenvalues are going to be real numbers. So you can arrange them in an order like this. There will be n eigenvalues if the matrix is n by n. That means if the graph has n vertices. The largest one, which is also called the spectral radius, if I am remembering things correctly, it satisfies these inequalities. Where little delta is the minimum degree of the graph, capital delta is the maximum degree, and some other such things are also there. Vaguely I am remembering some things. The chromatic number, I think this is the chromatic number of a graph. It turns out that this is less than or equal to 1 plus this maximum eigenvalue. Such very peculiar and interesting relationships are there. And this particular part where eigenvalues of matrices arising from graphs are investigated and seen what type of eigenvalues we get depending on what type of graphs we choose, and conversely, if the eigenvalues of a graph are given, that is, eigenvalues of some matrices related to the graphs are given, can we say something from those eigenvalues about the graphs themselves? That subject is spectral graph theory. Okay, it is also a very big, lively subject in which many things are being worked on. It's an active research area. So with that, this section ends. After this, there is one more section where the notion of graphs itself will be extended to such things as hypergraphs, multigraphs, that is graphs in which two vertices can have more than one edge between them, multiple edges, or in fact edges which start at one vertex and come back to that, loops. So we will see that in the next graph theory update. So I am ending the video here itself today, and tomorrow we are going to solve, let us solve again Gallian's problems on rings. So with that I wrap things up for tonight. See you tomorrow with Gallian's ring problems. Until then, this is me, Lucifer, from A Mathematical Truth. Have a nice night.